So we are going to talk about the basics of coordinate systems and space-time diagrams in special relativity. In order to do that, we have to start by talking about reference frames. A reference frame is a way that we can define a coordinate system in special relativity. We have to have a way to talk about when and where events happen, and that sometimes changes depending on which reference frame we're using. So we have to be sure to specify what frame we're talking about. Now, the way that we determine a reference frame is to take an object that we know is stationary in that reference frame, and that tells us the way that other objects are moving as well. For example, in my reference frame, I am not moving, so I am standing still. This whiteboard is also standing still, and the camera is standing still. But in my reference frame, if a car were to drive by me, that car would be moving. It would not be stationary, and so its x coordinate would be changing over time. Now, from the reference frame of the person in the car, they are not moving. By definition, their reference frame is the one where they are stationary. So as they drive past me, they are staying still, but I am moving in the opposite direction. So my x coordinate is moving backwards. Now, the type of reference frame that we talk about in special relativity is inertial reference frames. And an inertial reference frame is a specific type of reference frame where objects with no force acting on them have constant momentum. So Newton's first law of motion says that an object with no forces acting on it will continue in constant motion in the same direction until it's acted on by a force. So an inertial reference frame is a reference frame where Newton's first law of motion is true. There are also other reference frames. For example, if I jump off of a diving board, I'm accelerating down towards the ground. So from my perspective, all of the objects around me are accelerating upwards, despite the fact that there's no force acting on them. And therefore, as I jump off the diving board, because I'm accelerating, I am not in an inertial reference frame because the law of inertia does not hold in my reference frame. So we see in the diving board example that an accelerating reference frame is not going to be inertial. So for any two inertial reference frames, they will always be moving at a constant velocity relative to each other. Now we're going to talk about how we set up a coordinate system within an inertial reference frame. Now we know for any inertial reference frame that there's going to be some object that's stationary in that frame, and that's what we use to start setting up our coordinate system. We take some point that we define to be spatial coordinate 0, so x equals 0, and then we also pick a time that we set to be t equals 0. And those two choices we can take to be anything we want. After that, what we do is we imagine setting up a system of rulers and clocks. So we could imagine this is a really long meter stick, and at every single point, it gives us a measure of the distance from our original x equals 0 point. So anywhere we are in space, we can look at the ruler right next to us and say, look, this is how far away we are from that point. This is our x coordinate, this is our y coordinate, and our z coordinate. And along with the rulers, we're also going to have some clocks that we're going to put here that will tell us the time. Now, in our reference frame, in this inertial reference frame, we're going to define that all of these clocks are synchronized. So if I look at any two clocks, they're always going to show the same time in this inertial reference frame. In other words, if I'm standing still in this reference frame. Now we could talk about specific ways that we could synchronize the clocks in this reference frame. For example, you could shoot out a beam of light and you can calculate how long it would take to reach each of the clocks and then use that to set them so that they always start at the same time and then they stay synchronized. So within this system, we have rulers that give us the distance from any point back to x equals 0 as long as we're standing still. And we have clocks that give us the time, and all of these clocks are synchronized if we're standing still. Now the reason that I keep saying if we're standing still is it turns out that if someone is moving through this system of rulers and clocks, they will not observe that all of the clocks are synchronized. They will actually observe some of the clocks to be behind the other clocks. That's the reason it's important that we talk about which inertial reference frame are we using? Because these clocks we define to be synchronized only in the reference frame where someone is standing still relative to all of these clocks and all of these rulers. And that reference frame is what we use to define these positions and these times. Now we're going to talk about space-time diagrams, and this is a way to talk about the way that events happen over time at different positions. So space-time diagram is going to look like this, where we have on the horizontal axis some position value like x, and on the vertical axis we have time. But we don't just measure time, we actually measure ct, where c is the speed of light. So this gives us whatever time we have times the speed of light. The reason we want to do this is that distance is going to be measured in some unit like meters, whereas time is going to be measured in something like seconds. What we really want is for both of our axes to be measured in the same unit. That makes a lot of things nicer. So by multiplying by the speed of light, we get a measure of distance instead of time. Another reason this is nice is that we know any ray of light, any beam of light, is going to be moving at speed c. And so if we think about, over time, how is light going to move? Well, if the amount of time that's passed is 1 second, then a beam of light will have moved 1 light second, the speed of light times 1 second. So its x value is going to be something like this. But if we look at ct, of course, if t is 1 second, then ct is going to be c times 1 second. It's the same thing. And so for a light ray, it's always going to be moving at a 45-degree angle, or in other words, it's going to have slope 1 on this diagram. Now this line here is not describing just a bunch of positions in space. It's actually describing the movement of one single particle, that particle's one position, over time. So at every different time value, we see that this particle has a different position. So this line here is saying that a particle is moving in the positive x direction at the speed of light. So for every second, every vertical jump up, it's going to move 1 light second in the spatial direction. So within this diagram, this space-time diagram, every single point, every x comma ct, that gives us both a position and a time. So it tells us where and when something is. And any point on this space-time diagram we call an event. So an event is something that describes both the position and time of something. So any line that we draw in this space-time diagram, that gives us a sequence of events that tells us the position of a particular particle at every single point in time as we go along the line. One of these lines is called a world line, as it describes the motion of a particle over time. As another example, if we take an object that's stationary in our inertial reference frame, then on the space-time diagram, we're going to see that as a vertical line. Because as time progresses, the object doesn't move at all, so its position is going to stay as 0, but of course the clocks are going to keep ticking forward, and so we'll see the vertical line as time increases. If I were to move in the opposite spatial direction, then the world line might look something like this. Now notice that anything traveling less than the speed of light will have a slope greater than 1. And that's because if we take 1 light second up, it's going to move less than 1 light second in the spatial direction. So the horizontal value is not going to be as big as the vertical value. So the slope is going to look like this because the distance is increasing slower than the time is. That's what it means for the object to move slower than the speed of light. Now let's think about what the slope of this line would be for an object moving with velocity v. We know that the slope is rise over run, and that's going to be ct over x. Now, if we think about the velocity, that's going to be equal to the displacement over time. So we can write this ct over x as c divided by x over t, if we bring this t down to the denominator. And from there, x over t is equal to v. So this gives us c over v. That is our slope. So any of these lines is going to have slope c over v. And of course, if the velocity is less than the speed of light, then this numerator is going to be bigger, which means our slope is going to be greater than 1. And the slope is exactly 1 when an object moves at the speed of light. Now, so far on this space-time diagram, I've only drawn straight lines, meaning lines with constant slope. And we saw here that the slope gives us some measure of the object's velocity. So a straight line, a line with constant slope, is going to describe an object moving at a constant velocity. But if the object's velocity is changing over time, then this value c over v would not be constant. And so we could get a world line that looked something like this. If an object started to accelerate first in this direction, and then turned around and started going in the other direction, we could see a curvy line like this. Or we could see an object that goes all the way to a particular point over here, and then once it reaches a certain time, it turns around and goes the other direction. For example, if we shot a beam of light at a mirror and then it reflected back at us, the world line would look something like this. It first goes in the speed of light in one direction, and then it switches, goes at the speed of light in the other direction. One last thing I'll note here is that because our space-time diagrams have the vertical axis as the speed of light times time, it's often useful, instead of talking about the velocity, to talk about something where we use the letter beta. This is the velocity divided by the speed of light. Or in other words, x over ct. So you can see that if we go over here and think about the slope, which we know is rise over run, ct over x, that's going to be 1 over beta. So the slope of any world line is going to be 1 over beta, where beta gives us the object's velocity as a proportion of the speed of light. For example, if I got in a spaceship and started moving at 1/5 the speed of light, so my velocity is 1/5 c, then my beta value would be 1/5. And from that, we could get that my slope on the world line would be equal to 5. So the world line would look something like this. So that is how we use space-time diagrams to describe a sequence of events in an inertial reference frame.